Alright, so as I was saying earlier, y is equal to a sine omega t becomes the displacement equation at any time t. Okay, we can, if we consider the displacement, and here it is y because we are considering vibration or oscillation along the y axis of the, we are considering oscillation of the body along the y axis. If we are, let me just adjust the board a bit. If we are looking at oscillation along the x axis, that is, we are looking at the displacement equation of the body along the x at any time t, then we have to find this component of x. And as we use in trigonometry, whenever we are using for or looking for adjacent or horizontal, we use cosine. So cos of the angle omega t, which is equal to the adjacent or the horizontal divided by the hypotenuse, which is the amplitude A. R is equal to A. Then we have x is equal to A cos of omega t. And this is the displacement equation at any time t along the x axis. Okay, so A sine omega t is a displacement equation along the y axis. A cos omega t is a displacement equation along the x axis. So when we are looking at the displacement, the body is moving and then we are tracing its position on the x axis. Okay. When it comes to this, we realize that as the object moves, the body will be oscillating horizontally. Okay, and this will be the equation for the displacement at any time t. All right. Okay. Now let's also look at a general. If this is it, then I want us to come out with some findings, which even can be seen from the diagram, but I'll take you through it, and after that we'll use the displacement equation to prove what we just observed. And doing so actually will help you understand the concept so well. Okay, so what I've done is that I've divided the time. Of course, we are saying that for one complete revolution, the time taken to do so is a period, capital T. Let's break this period into quadrants. So for one quadrant from here to here, T on 4, period T on 2, 3/4 of the period, and then back to T. So 0 and then T. Now I want us to look at the displacement of the particle along the y-axis. So along y, that's why I'm dipping the line. At time t is equal to 0, what is the displacement along the y-axis? I think you all agree with me that when we trace this point to this point, it is 0. Okay. When the object or the body moves and then comes here, at time t is equal to quarter of the period, what is the displacement of the particle? When we trace it, this is it. Meaning it has used the time t on 4 to move from here to this point, and its displacement will be the maximum displacement, which is the amplitude. Alright. Now, at time t is equal to period on 2, what is the displacement of the object on the y-axis? So, when the object is here and we are looking for its displacement is 0. When you trace, this is 0. At time t is equal to the period on 3/4 of the period. When we trace the displacement of the particle on the y-axis, it will give you the maximum y value, which is also the amplitude, but in the opposite way. So over here and over here, we have the maximum displacement. Y is equal to A. When the body moves from here back to its starting point, okay, and this is complete revolution, so big T. Okay, what's the displacement? When you trace this position on the y-axis, it is also 0, meaning from here to here, okay, the displacement is 0, but from here to this place, the displacement is according to the maximum amplitude. Don't forget, we are looking at displacement along the y-axis. Okay, we will later on look at what happens along the x-axis. So let's use mathematics to picture the same thing. We are saying that the displacement equation at any time t is equal to